Good afternoon, and welcome to the session on the characterization of treaty-relevant events. My name is Mario Zampolli from IMSED at CTBTO, and I'm co-chairing this session with two dear colleagues, Dr. Mohamed El Gabri from the Egyptian National Data Center and Dr. Bocelou, Radionuclide officer in IDC. Without much ado, we will start with the first presentation, which is from Anton Ziolkowski from University of Edinburgh, and it is about Bayesian inversion of nuclear of recordings from nuclear tests from the DPRK. Please, Anton.
Thank you very much. Good afternoon, everybody. It's a great honor to be here. One thing about explosions on land is that there is nowhere that you can put a seismometer and get a clear measurement of the source signature. So this is about getting source signatures. Let's go back. So here's a map of the Democratic People's Republic of Korea. The yellow star is the test site, and the red triangle is a seismic station in China, Wudanjiang, and it's 373 kilometers north of the test site. So from the seismograms recorded at MDJ, the goals are to recover the source parameters and source time functions of the contained explosions, and the Green's function from the DPRK test site to MDJ. So here's an outline of my talk. I'm going to say what is meant by contained underground nuclear explosions. I'm going to describe the method which was actually published a year ago in Geophysical Prospecting when I looked at explosions from small charges of about a kilogram, so more than 6 orders of magnitude smaller than the explosions at the DPRK test site. But I'm going to use the same model, Blake's 1952 source model, except that because these explosions are shallow compared with the radius of the nonlinear zone, you have to include the free surface. In the abstract, I said that I would do a grid search to find the parameters, but there are too many parameters for a grid search, and so I have to use very fast simulated annealing. Then I'll show some results. The Green's function to Wudanjiang from the test site and the source time functions. Then I draw some conclusions. So here's a slide from Steve Myers. So he presented a talk in Edinburgh in 2019, a great talk about these tests. And here, Steve and his team at Lawrence Livermore have located the 6 tests at the DPRK test site. And the one on the right, I don't know if this works. So test site 1, test 1, DPRK1 leaked radionuclides, and so that was not contained. But all the others, 2, 3, 4, 5, and 6, they're clustered together on the left. They are contained and did not leak radionuclides. And I want you to notice the scale of 1 kilometer there, and you can see that that little cluster on the left, that all those events are within about a kilometer of each other. So it's another slide from Steve Myers. I'm very grateful for this. So on the left-hand side, you can see the seismograms of the 6 tests recorded at MDJ. And they're all normalized to maximum amplitude. And you can see they're very similar up to really where the Rayleigh wave comes in, about halfway along. And then on the right-hand side, you can see them plotted on the same scale, and you see that the sixth one, which is at the bottom, so the first one is at the top, and then they go down, and the sixth one on the 3rd of September 2017 is much bigger than any of the others. So I'm just showing you here 2 seismograms of the first 10 seconds of DPRK2 and DPRK3. And you can see that DPRK2 in black is smaller than DPRK3 and slightly higher frequency. So this is a method. So we know that the contained explosions are all within about 1 kilometer of each other. So the path from each explosion to the MDJ seismometer is the same for each of these, more or less. So there's one Green's function from each of those, from those explosions to the MDJ seismometer. So I'm calling it G of T. And for the ith explosion, the seismogram is X sub I of T is the convolution of S sub I of T, the source time function, with the Green's function, plus noise, Ni of T. So the noise is different for every explosion. So we model Si of T and find its inverse filter Yi of T from the equation Si of T convolved with Yi of T is approximately a delta function. And then we estimate the Green's function by convolving the inverse filter with the seismogram. And that's shown in the second equation. And we get an estimate of the Green's function. We don't get the Green's function because we've just got the inverse of a modeled source time function, which may not be the right function. So we then adjust the source parameters to minimize the differences among the different estimates of the Green's function. And when we've minimized it, then we've got the answers. That's the idea. So when the explosion is detonated, it vaporizes the rock. And then beyond that, it melts it. And then beyond that, it fractures the rock. And eventually, at some radius, the propagation is elastic. And only about 1% or less of the total energy is converted to seismic waves. And the other 99% is in that nonlinear zone, destroying the rock. So Blake's model, he replaced the nonlinear zone surrounding the explosion by a cavity of radius A with internal pressure P, well, a step function. And he placed it in a homogeneous isotropic elastic medium. So there's his model. So actually I can hardly, I've got glasses, but I can hardly see that, so probably you can hardly see it either. But there's a velocity potential phi, and it's 1 over r times some function of tau, and tau is equal to t minus r minus a upon c. And the velocity that propagates has 2 terms, a 1 over r squared and a 1 over r term. And the source time function for this is called the reduced velocity potential, which is f of tau when r equals a. And I've also shown another equation at the bottom, which is the pressure, which turns out to be a 1 over r function. Now, the first explosion leaked, so it was close to the surface. So all these other ones didn't leak, but they can't be that far from the surface. So we don't know how deep they are. And so we say we have an unknown parameter, and I'm calling it f, and f times a equals h, the depth. So there's a lot of, the key parameters that we need to find are the resonant frequency, Poisson's ratio, this depth factor f, and the tensile strength of the granite at the radius A. So at the top, I've got an equation that relates the internal pressure to the external pressure, including the overburden pressure, plus a reflection from the virtual source. Now, Mount Mantap is a granite peak. And so granite is granite, so people have measured it all over the world, and I'm taking some numbers from the literature. The density is 2,690 kilograms per cubic meter. The bulk modulus is 5 times 10 to the 10 pascals. Now, normally, it will have a Poisson's ratio of 0.25, but when you fracture it, Poisson's ratio increases, and then the velocity decreases. So in practice, we're going to use 2 sources, so 4 parameters per source. So I mentioned very fast simulated annealing, and it's described very well in the book by Sen and Stoffer. So basically what we do at each iteration, each parameter is selected at random from its range, and you have to define the range. Then you can calculate the source time function. The Green's functions are obtained by deconvolving the seismogram for the source time function. And then the normalized root mean squared difference between the 2 Green's functions is the error. If the error is less than last time, we have a new model. If it is greater, we accept it with a reduced probability, and at each iteration, the temperature is gradually reduced until you converge. So I've left out lots of details, but here are the recovered Green's functions. So from top left, we have that's the Green's function for the second one, dPRK2. Then in the middle at the top, dPRK3. On the right at the top, dPRK4. And at the bottom, dPRK5, dPRK6. So these are all Green's functions, all plotted on the same scale, up to the Rayleigh wave. And you can see that they are very similar to each other. So all on the same scale. So taking the same 2 seismograms I had before, so the top picture there is the seismograms I showed you before, dPRK2 and dPRK3. And underneath are the recovered Green's functions. And you can see that they are basically wiggle for wiggle on top of each other, almost. They're not exactly the same, but they're very, very close. And here are the recovered source time functions, individually scaled. And it's the same numbering, so from top left, dPRK2, and going across to the right, 3, 4, and then at the bottom, 5 and 6. Now, if I plot those on the same scale, we get this, and you can see that that last explosion is so much bigger than all the others. And that hole in the middle of the peak is a reflection from the surface. So then you can get parameters. So once you've got these parameters, you stick them in the program and you calculate the source time functions. So you can see the top row, elastic radius in meters, ranging from 141 meters radius for the smallest one to 463 meters. I mean, probably that 3 isn't right, but that's, maybe it's within 10%. 3%, okay. So that radius is really interesting. So here are the 5, 2, 3, 4, 5, and 6 explosions. There's the kilometer scale, and then here are the radii on the right-hand side. So let's see what happens. So that's the nonlinear zone around the second one. That's around the third one. That's around the fourth one. Now, there's no room for that sixth one, is there? So all that granite is destroyed. So we have extracted estimated source parameters and source time functions of the dPRK contained underground nuclear tests from 2009 to 2017 from the seismograms recorded at MDJ. The recovered Green's functions between the DPRK test site and MDJ are very similar but not identical. The recovered source time functions can be used to estimate Green's functions to other seismometers. And the two 2016 tests, DPRK4 and DPRK5, created weak fractured zones close to the site of DPRK6, causing it to behave differently from the other explosions. So I thank Steve Myers for permission to use slides from an excellent talk he presented in Edinburgh in 2019. Excuse me. I thank many friends and colleagues with whom I've discussed this work over many years. And finally, I thank the CTBTO for accepting the paper, for providing the funding to enable me to present it here, and a lot of other help I had along the way as well. So here are my references, and I thank you for your attention.
Thank you very much. We have a short time maybe for one question before the next talk starts. And I may ask the author of the presenter of the next talk to come forward already. Yes, I see one question back there.
Hi. The method relies on the Green's function for the 6 events being similar. Do you have any feeling for the spatial scale over which that would begin to break down? If there were a 7th one, heavens forbid, how close would it have to be before you could become part of your same data set?
So normally you would say that the source has to be, so the distance between the sources would have to be small compared with the wavelength. Now, what I found is that what I found is I've got a cough. No, what I found is at the resonant frequency, the wavelength that corresponds to that resonant frequency is equal to the circumference of the nonlinear zone. Oh, thank you very much. And so you can't say the source is small compared with the wavelength, but that gives you an idea of the wavelength. So the resonant frequencies were between 5.6, I think, for the smallest one, and 1.6 for the largest one. The velocity is 5,000 meters a second, roughly. So I think 1 kilometer is, they're pretty close together. And in fact, as we see, some of them actually overlap with each other. You can't get closer than that. Right.
Thank you.
Thank you so much. Please.
Thank you. And right now, we introduce the second talk. We have an interesting talk about collapse events and treaty monitoring from Lawrence Livermore. The speaker will be Michael Pasyanos. You have the floor, 13 minutes for the talk and 2 minutes for discussion.
Okay, thank you. Good afternoon, and I'm pleased to share with you some research that I've done recently with my colleagues at Lawrence Livermore National Lab, Gina Chinose, Bill Walter, and Sean Ford. So, why study collapses, right? Aren't we interested in explosions and nuclear explosions? Hopefully I'll address that. And then I want to kind of briefly talk about the physical mechanisms involved here, and then our efforts to develop a global collapse database. And then I'm going to turn to some of the analysis we're doing, including full moment tensor solutions, S-wave amplitudes and spectral ratios, coda analysis, and then discuss collapse volumes. So, why study collapses? Well, there are a lot of things out there, and we see collapses quite a bit when you look for them. And they're particularly challenging because, like explosions, they tend to be shallow, and so they confuse a lot of the discriminants or identification methods we use for identifying explosions. And a good example of that is if we look at the MBMS discriminant for this large data set that we've been assembling, we fail the event screening 44% of the time, so about half of the time. So we need to be concerned with them as a population. So, but oddly enough, so there's sort of 2 types of collapses I'm going to be talking about. The first are related to mine events, and the others are related to nuclear explosions. But addressing for the moment the mine event ones, what we actually see in the Earth is often these mine events are explosive in origin, right? So you could tell by the name: rock bursts, pillar bursts, coal bumps. So the initial motion might be an explosive element, but then that's quickly followed by, if you look at the B up there, once that pillar is gone, then we're going to see a large collapse, reduce the void, and that's what we're going to observe in the far field. And of course, when we have voids created by nuclear explosions, we're also going to see that void, that collapse. So we've been kind of marching around, and when we can identify collapses, we've been analyzing them as much as possible. And right now we're at 43 events for which we've identified collapses and are able to do a full moment tensor solution on that. And I'm going to be talking about the moment tensor solutions in a second. And as I said earlier, some of them, such as the ones in Nevada and North Korea, are associated with nuclear explosions occurring 20 minutes or maybe the next day after an explosion. But most of them, for the most part, are related to mining activities. So I'm on the hunt. So if you know of any good collapses to look at, please talk to me or send me an email afterward. You can see, except for South America and Antarctica, we pretty much have every continent covered. Okay, so moving on here. This is a typical moment tensor solution for these events. This happens to be a mine collapse in Russia. It's hard for me to see. I think it's 5.2, more or less. You can see that there's excellent fits. If we look at the beach ball, it's all implosive. And if you look at where it falls on the fundamental loon, one of the reasons we need to do a full moment tensor is if it was just DC, it would plot in the center of that diagram. If it's a deviatoric, it would plot along the equator. By doing a full moment tensor solution, we can kind of explore the full model space. And in this case, and in most cases, the events plot near the negative crack mechanism. So we have established an identification method that follows the procedure that was used for an identification method for nuclear explosions. And so what you do is you calculate the distance of, you calculate the centroid of a population on the hypersphere, so the 5-sphere of the moment tensor. I'm showing you the fundamental loon, but the actual discrimination is done in the hypersphere. But what you do is for, say, the explosion population, which is shown in red and orange, calculate the centroid of that. Similarly with the collapse population, which is shown in gray and black to the bottom right. And so any new events, such as the green ones, this data set is in the Western United States, we calculate the distance on the hypersphere to those populations, and based on that, develop a screening criteria. So if we do that, a key question is, what is your screening angle? Because even if you calculate the center of the population, if your angle is 0, you're not going to capture any of the actual explosions. But when you go to a reasonable screening angle, say 40, 50 degrees, you're capturing most of the explosions. But of course, if you make it too large, you're going to start capturing some of the presumed earthquakes. And we can do the same thing on the collapse side, which is shown figure on the right. So the earthquake population tends to be farther away from the collapses, and so we could actually have a larger screening angle and still be able to capture all of the collapses without misidentifying some of the earthquakes. And lastly, I will say for the Western US data set, if we exclude events in the geysers, this is a geothermal region, which actually has production. Those are actually positive cracks. They look very much like explosions. You'll get the improved screening angle that's shown by the green dashed line for the earthquakes. So actually, bottom line, we have an identification method with basically 98% accuracy if you can calculate a full moment tensor solution. But there's other methods. One method that's useful for explosion earthquake identification is P to S ratios. But you can see the green symbol on the figure on the left is the 2017 collapse after the DPRK test, and it doesn't do a very good job looking at P to S. But if you look at the ratio of a lower frequency S wave to a higher frequency S wave, this seems to be a very good way of identifying collapses, with a caveat I will tell you in a second. So if you plot both discriminants together, you can see that the source populations basically reside in different quadrants, with earthquakes to the lower left, explosions to the upper left, and collapses to the right. And if we look at other events and other stations, here we're showing ELCO, which is looking at not only post-explosion collapses at the test site in Nevada, but also mine collapses in Utah and Wyoming. It does have a high discriminant here, but if you look at the figure on the right, it only seems to work. This is a plot of the Mahalanobis distance, which is the separation between the two populations. It seems to work well for shallow collapses, but not so well for collapses that we believe are deep. So one way of kind of getting at this a little bit further is, rather than just look at some part of the spectra, we could actually look at the whole spectra. And that's the goal for doing coda analysis on these events. So what we can do is, using a coda method, which has been well established, and we actually have a tool that you can use to develop calibrations and look at the source spectra, you could not only accurately determine the size of an earthquake, the moment, but you can look at the corner frequency. And in the example I show here, it's about the same size event, but the event in the geysers has a much lower corner frequency and a much lower stress drop. The advantage of doing that is there seems to be some differences between earthquakes and the Brune-type spectra. So you have a long period level and then a corner frequency. Explosions seem to look different because they're shallow. And so the figure to the right shows spectral peaking that seems to be related to the absolute depth of the event. And so it's our expectation that when we start looking at collapses, we're going to see something similar. And so the last thing I want to look at is, can we estimate the volume of collapses? So we want to do this in both a reflective manner, but also in a predictive manner. So we're going to follow the procedure used by Ford et al. in 2008, in which the collapse is modeled as a gravity-driven, horizontally lying vertical closing crack. And so if you know some information about the source, the material properties, as expressed in the Lamé parameters, you can get an estimate of the S and the U, so the area and the average closure. And so we have a large data set for which to test this out. And in a few cases, we have independent estimates. So we're going to look at those. The first example is from the underground nuclear explosion at Trisco that occurred in 1982. For this event, it had an announced yield and an announced depth. And so using Denny Johnson, we can estimate a cavity radius and, of course, get a cavity volume from that. And when we do our moment tensor analysis, it comes out to about 50% of the total cavity. So do we know if this is right? No, but it seems like a reasonable estimate here. In the other cases I'm looking at, these are compared to other people's estimates. So this is the largest event in our collapse database. It has a collapse volume of 4E6 cubic meters. But other estimates from Dave Bowers and Bill Walter, based on other people's parameters, put it in the same ballpark. And you can see the moment tensor fit there. As we go forward in time, we're going to get, and we start going into the United States, where we have much better coverage. You can see that these moment tensor solutions, first of all, are high quality, right? So we often have to throw out events just for, throw out stations just for convenience. But, so this is a 1995 Solvay, Wyoming mine collapse. And again, you could estimate, or you could compare the moment tensor collapse volume to the other estimate from leveling data. And you're not supposed to see this other than this is during the US array transportable array. So we're swimming in data. We have very confident estimates. And there's a lot of variation in the estimates here, but it seems somewhat consistent with them in total. And then coming back to North Korea here, we have a moment tensor analysis of the collapse volume. And again, there's a number of different estimates, but it seems within the ballpark. So this seems a reasonable way of predicting the volume. If we compare all of these, yes, thank you. It seems to be a reasonable estimate. There's a less than a factor of 2 deviation in our comparisons to the other comparisons, which of course in most cases are not a ground truth estimate. But there are more events out there to look at, especially nuclear explosions. We're using legacy data to kind of get at more events, and we'll be able to do the same analysis that we were able to do for Etrisco. And kind of as a summary, and then I'll kind of show you what we're heading to next. The basic story is for treaty monitoring purposes, we really need to kind of identify collapse events because they are nuisance events and they can be confused with explosions. I'm not going to go point by point through this, but I will kind of say in the future, we're driving towards a development of a collapse source model, similar to an explosion source model like Mueller-Murphy or Denny-Johnson, where the long period level would be related to the collapse volume, the spectral peaking would be related to the absolute depth, the corner frequency might tell us something about the collapse time, and the high frequency roll-off can tell us about material properties. So thank you.
Thank you. We are running out of time, so one question, if any. So I believe you will be flooded during the coffee break with questions. Thank you a lot. Mario?
Yes, so we go over now to the next presentation, which is from Josphat, Kyalo, Mulwa from the Kenyan National Data Center, University of Nairobi. And we will hear about systematic seismic events discrimination at the Kenyan National Data Center. Please, Dr. Mulwa.
Yeah, thank you very much. My name is Josphat Mulwa. I'm from the University of Nairobi. So today I want to present you some systematic seismic events discriminants used at Kenya National Data Center. Okay, so the outline, I'll present some background information, then I'll give some seismic event discriminant methods and their ranking at our NDC. I'll present some examples, then I'll conclude and make some recommendations and acknowledgements. Next slide. Next slide. Yeah, so here I present you a very nice map showing the seismicity in the East African region for the period 1900 to 2020. And the big question is, from those earthquakes, are we able to tell which are natural and which are anthropogenic? So we know that at the IDC, they routinely apply event screening to discriminate events using more technology approach in order to characterize events. But at the Kenya NDC, we have adopted a step-by-step procedure for event discrimination, and which we apply routinely. And so the aim of this is to get results in a short time. So we are looking at a method where we can get results within a very short time. Yeah, so here I present you some of the discriminants. The previous presenters have presented a wide range of discriminants. I also present the same, but I'll not, we don't apply all of them because, as I've said, we only use those which can give us results within a very short time. Not that the others we can't use, we can also use, but if you have to report quickly, then it's important you make your selection. So event parameters, hypocenter, epicenter, we know that depth is the first order discriminant, because if your event is 30 kilometers, then do you need the other discriminants really? Then magnitude, according to IDC rules, if an event is less than 3.5 kilometers, then again, you don't need to bother with that one. Then next, we apply, we relocate the event just in a bid to refine the depth. Then we use MBMS criteria, and then we determine focal mechanism. So the other discriminants which exist in literature are short period discriminants, which range from complexity, spectral ratio, third moment of frequency, regional PS ratios, amplitude ratios, LG spectral amplitude ratios, Corda decay, which the previous presenters presented, moment tensor inversion, as well as waveform modeling. Next one. Okay, so here, back one slide. Yes, so here I present you one of the events which I'm going to present as an example. This was in 2019 in the southern part of Kenya. So we have used NDC in a box, and the larger map shows the location, and then the inset map shows just a refinement of that location. Next one. And then the other one is another one in the northern part of Kenya in 2020, May. Again, you will observe that all the depths are 0, because for some reason, NDC in a box will give you a depth of 0. Next one. Yes, so now for the 2019 event, on the upper part, that's what has been refined using hypocenter, and then on the bottom part, that's the initial solution using the NDC in a box. So from the depth here, also we can see NDC in a box is giving a depth of 0, but then when you refine that using hypocenter, it gives you a depth of 9.1. Now there is a depth rule which I'm going to present shortly. Oh yeah, it's bottom here. So if the depth is greater than or equal to 10, that's most likely an earthquake. So in this particular case, it's less than 9.1. So at this stage, we cannot really tell whether it's anthropogenic or natural. Next one. And then this is 2021 in May 3rd in the northern part of Kenya. Again, NDC in a box solution, again depth of 0, and then when you refine that using a hypocenter, then you get a depth of 14.1. So we can stop there and say, oh, this depth is more than 10 kilometers, so we can categorize this as an earthquake, and then we move on. So next slide. So the other criteria we use is MBMS criteria. So I present you some diagrams which exist in literature from the IDC. And the right one shows the distribution of events from former testing. And so we use a formula for the IDC, 1.25 MB minus MS. Sorry, back. No, next one. Yeah, so we use the formula 1.25 minus MS is equals to 2.0. So that's the formula in the IDC, and For an explosion, then MB has to be greater than MS. And so you can see here for both of these events, which I'm using as an example, then the MB is greater than MS. So do we stop and rule them as anthropogenic, or what do we do next? So next one. Okay, so the next phase is to determine their focal mechanism using FOCMEC. And so this displays a double cover earthquake focal mechanism. It performs efficient systematic search of the focal sphere, and then it reports acceptable solutions based on some selection criteria. And the source is quoted there. So next one. So this image here shows the focal mechanism for the two events in the 2021 and then the 2019 event. And purely, this is a double couple focal mechanism, and we can confidently say these were natural earthquakes. But what we note is for the northern one, the one in the northern part, that's a combination of strike-slip faulting, strike-slip faulting and normal faulting. But in the southern part, we see more of strike-slip faulting. That's still puzzling to us, and we are doing more investigation on that. Next slide. Okay, so what do we do in the event of indeterminate solution? So you have gone through the 4 or 5 discriminants I've mentioned. So we go back to our MBMS criteria. And now instead of using the conversion formula, we simply measure the amplitudes. And then we use the formulas by, Gutenberg to calculate MB and MS. And that's more accurate than the regression equations which we use to convert magnitudes. Next one. Okay, so here I just present you an example. It's of an earthquake whose MB and MS magnitudes were determined using the amplitudes for the surface waves and body waves. So this was not in Kenya, it was actually outside Kenya. So I'm just presenting it as an example. So once you measure your amplitudes and the period, then you can use the formulas by Gutenberg, and you are able to calculate your body wave magnitude as well as MS surface wave magnitude. So we did not apply this for the 2 examples I've shown you because we did not download, or rather we did not request the long period components. So we were just using the broadband and short period components. Next slide. Okay, so in conclusion, so we note that a variety of methods and techniques for seismic events discriminants are available for NDCs. And at our NDC, we have developed a hierarchy of seismic events discrimination. And we use moment tensor inversion as well as waveform modeling as our expert technical analysis. Now, as our recommendation, we are recommending that IDC considers incorporating seismic event discriminants in the NDC capacity building trainings. And so some acknowledgements. So through collaboration of the CTBTO and the Building Research Institute of Japan, as well as the International Institute of Seismology and Earthquake Engineering, with support from JICA, they have been conducting trainings on knowledge co-creation, global seismological observation. So this training was provided by them, and that's why I'm making a recommendation that CTBTO can consider incorporating that also in the NDC capacity building. So we are really grateful to the PTS as well as the various institutions in Japan with funding from JICA. Thank you very much.
good afternoon and welcome back after the coffee break. If you may have your seat in order to proceed with our second half of the session. In this half of the session, we have two presentations. The first presenter is Aurelie Guilhem. I hope I pronounced it right. Her presentation about using moment tensor inversion for rapid seismic source characterization from nuclear and regional seismicity monitoring to tsunami warning. You may have.
Thank you. Hi, my name is Aurelie Trilla and I'm a seismologist at the French NDC, CEA. So I want to talk to you about the complete source characterization for event screening, or rapid event screening. So the complete source characterization of an event can take from So I start again. The complete source characterization of an event can take from a few minutes to a few hours after an event of interest, and it can actually take several days also. So by that, I am talking about the detection of the event, its location, its magnitude estimation, but also the mechanism of the source. And the source mechanism, the very last step, is very important because it helps constrain the fault motion after a significant earthquake. It can also confirm the nature of an event, whether it's a nuclear explosion or an earthquake. And it can also define the moment magnitude, MW, that is linked to the energy of the source. But this very last step is actually something that requires most often the need of a senior seismologist or an expert to calculate waveform inversions for the determination of moment tensor. And so here I want to show you a way to generalize moment tensor inversions for the source characterization to be done in a very rapid and easy to use algorithm for different purposes, for earthquake monitoring, but also tsunami warning, and last but not least, nuclear explosion monitoring. So this can be done using GridMT, and GridMT was proposed about 25 years ago by Kawakatsu. It's a very simple approach. You have a grid of virtual sources. Basically, it's a potential location of a seismic event for which you are computing continuously moment tensor inversion on a long period data. It's very rapid because you use predetermined inversion parameters and you also use a catalog of Green's functions. It's a simple approach. It provides all the source information at once in one unique algorithm. You get the origin time of the event, its location. You also get the moment magnitude, the source mechanism, and the source decomposition. And it's very interesting because you can implement it in near real-time system for earthquake monitoring or seismic event monitoring. However, it has some limitations. You need to have a fixed grid of sources, and you also have to have a fixed and limited number of stations. And it also requires a very important moment tensor work for parametrization. It has been already used, tested, and implemented in different regions, mostly for earthquake monitoring in Japan, in Taiwan, in Northern California, in Alaska, so in very active tectonic regions. We also tested it in the Swiss mountains for the detection of rock slides using seismic waveform signals. And it was also used by Nayak and Draeger for detection and characterization of seismic events linked to a sinkhole formation in the US. So let's go back. So here at the French NDC, we want to focus on 3 different regions: North Korea for monitoring of explosions, France for the detection of earthquakes, and also in the Mediterranean Sea for tsunami warning. So let's start with North Korea. So we have had in the past very successful moment tensor inversions that were obtained for all the DPRK explosions. So we use this knowledge to implement and configure the GridMT system for North Korea. From the 8 regional stations that were used for specific moment tensor inversions, we decrease this number to only 4 those 4 stations you see here on the map by the red triangles still give us a correct azimuthal coverage of the grid. And the grid is composed of nearly 1,200 points, spaced every 0.2 degrees in latitude, and we only focus on shallow seismic events, so the grid is at 1 kilometer depth. And for each point of the grid and every second, we actually compute full moment tensor inversions. So I'm going to show you an example for the 2009 DPRK explosion by showing you 3 different time periods. One starting 30 seconds before the explosion, one that is obtained 1 second after the origin time of the event, and one other 30 seconds after that. At the bottom, you see the vertical traces filtered at long period for the 4 stations. And grid empty is inverting for the 3 components of the 4 station, but I'm only showing here the vertical components. In the very first time window, what you see is a bad agreement between the data in black and the synthetics in red. None of the points of the grid actually can fit those waveforms with a high level of confidence. And the misfit functions is expressed by the variance reduction, VR. The center figure shows the best time at the time where we get the best variance reduction value. And it actually is centered underneath the Pyongyori test site. We see that we get a full explosive mechanism, and the waveform fit is very good. And at the end, 30 seconds later, even so, we still have the waveforms of the explosion within our time window. None of the points, again, of the grid can actually explain this event. And so what we are actually looking at, it's the time evolution of the VR, and we want to find a peak in this VR function. And the peak of this VR function actually gives us all the information of the event. Its location, its moment magnitude, its source characterization, and decomposition. So we applied it on a long-term analysis for North Korea by considering all the DPRK explosions shown here in red in the middle plot, but we also compared it with regional and local seismicity from the French NDC catalog down to magnitude 2.5, and also from the EMSC catalog down to magnitude 4.5. And some of those events at greater depths, very important depths, more than 300 kilometers. What we see is that all the explosions basically will reach very high value of VR, nearly 80%. So we get a detection of those DPRK events, but for all the other tectonic events, actually the VR stay low, below 40%. So basically this implementation here only allows the detection of the DPRK explosions. We also get the detection of the 2017 collapse. As you see on the top figure, this event followed 8 minutes and 30 seconds later, the largest explosions on the Pyongyori test site. For this one, the VR value is smaller, but this is because at long period, we are still in the coda energy of the large explosion. But we still get implosive mechanism in agreement with the collapse and a correct magnitude. So from that, we moved on and wanted to have an interactive tool for the CA analyst so that it becomes easy to compute very rapidly moment tensor inversion. So this is the example of what that could give. It's basically the analyst only has to enter the time period he wants to look for an event, and the code does the rest. The results are obtained within a few minutes only, and basically does everything. It downloads the data, processes the data, so removes the instrument response and filters them. It does the thousands of waveform inversions, and it finally plots the results. So far, we can use 2 sets of stations, including station from the IDC and from IRIS. And it's, as you see, a very easy to use interactive tool. The detection of an event, of a potential event, is given on the top. You also get the map view to have some understanding of the confidence you can have in the solution. we get a beach ball representation as well as the Hudson representation for the source characterization. And that's something that we want to move for real-time processing, but it's not done yet. Now I'm going to show you a second example. It's for regional seismicity in France. So we did the same work, and we implemented a large grid over southern France. This time we used different depths too, and we got correct detection and characterization for all magnitude 4.5 plus earthquakes in these regions, including the Le Tail earthquake that occurred in November 2019. It was a magnitude about 5. However, we reached some difficulties for the lower magnitude earthquakes, as a magnitude 3.8 earthquake in the Alps, the Tonon-les-Bains earthquake, for which we actually need to have smaller grid surge, smaller epicentral distance, and also we need to look for higher frequency signals. But once this work is done, the grid MT performance increased by a lot, as you can see here. And finally, the last point I want to make is that grid MT can be used for tsunami warning. At CEA, we host the Tsunami Warning Center that is called CNALT. And the CNALT has a mission to monitor 24/7 large earthquakes in the Mediterranean Ocean, Sea, and the Atlantic Ocean. And it has to warn within 15 minutes the authorities, the French authorities, and the population of the danger of a large earthquake that could potentially trigger a tsunami. And so we wanted to test the feasibility of using grid MT for such approach, given that grid MT is a rapid tool. And so we tested it for a region here, shown here, in the Maghreb margin, where there are large earthquakes, possibly large earthquakes that can trigger tsunamis. So we looked at magnitude 4.5 earthquakes and larger size since 2016, including the Alosaima earthquake in 2016, a magnitude 6.4, as well as a Beja earthquake in 2021. And those two events here I'm showing to you did trigger a small amplitude tsunami waves on the French coastlines. And so overall, we obtained good results for both detection, locations, magnitude, and mechanism estimation. And why is it important for CNALT? It's because grid MT result can be obtained within 10 minutes, which is less than the 15-minute time frame it has to provide an information to the authorities. And if we get the good magnitude and a correct estimation of the focal mechanism, we can use that as input for tsunami modeling and have more accurate wave height estimations. So it was just a study for feasibility analysis of grid MT for this purpose, and we are to move forward for implementing it in the real-time operating system of the CNALT. So in conclusion, I try to show you that grid MT is a very rapid approach. We get results within a few minutes. We can calculate thousands of moment tensor, and this is done using a regular workstation. No need of parallel computing or high computing system. It's a unique algorithm that provides all the information, but you need to do very intense parameterization work. It can be implemented in real time or near real-time automatic system, and that's actually the way we want to move on at CEA. And finally, I try to show you that we can use it for various applications. I show you 3 of them, where we can open the possibilities for induced seismicity, volcanic monitoring, and so on. With accurate setup, once again, we get the correct detection and characterization of the DPRK events, but also earthquakes in France and for tsunami warning. The tool is very easy to use. The results are obtained in a few minutes. So it helps us to actually have better constraint in case of an event of interest in Korea, where basically we can have a very rapid event screening. And finally, I didn't show it to you, but we can open the possibility of estimating the uncertainties from the moment tensor inversion here, because we have thousands of solutions per time steps, and then at the end, we could actually have uncertainties on the location, magnitude, and focal mechanism, and also the nature of the source. So with that, I thank you, and I If you have any question, you can also send me email. Thanks.
Thank you for the very nice presentation. We are open for questions, if any. I don't see for now, but I believe you are happy to receive them by email as well. So thank you very much.
Thank you.
Thank you.
Next talk will be given by Eric Pili. His title is STM Toolkits, a radionuclide source term modeling package for rapid scenario determinations and French NDC. Now, floor is yours.
Thank you. First, I would like to thank my co-authors as well as the students who worked on this project. Let's start with some keywords about the detection of underground nuclear explosions from the monitoring of radionuclides, as it is done in some NDCs. Everything begins with some atmospheric release of radioactivity, aerosols or gases like radioxenon, either in the form of early venting or late-time seepage. Due to atmospheric transport, this radioactivity is likely to be observed by a monitoring system. If so, according to certain criteria, then we use backward ATM, backward atmospheric transport modeling, to verify that the source region is consistent with a nuclear test site. Then forward ATM is used to quantify more precisely and predict when, where, and how much radioactivity could be detected at the monitoring stations. However, forward modeling needs an atmospheric source term, which is unknown. The nuclear cavity contains gases and aerosols, including radionuclides and H2O vapor under pressure, and the cavity source terms result from many physical and chemical reactions, processes that I will not detail here. Some radionuclides can reach the atmosphere thanks to borehole or a single fracture or a fracture network. Then subsurface transport is also a complex physical process that will control the migration of the radionuclides. As a result, the atmospheric source term is different from the cavity source term, and its determination is not straightforward due to radioactive decay and Doppler products, fractionation processes of elements and isotopes, time-dependent gas fluxes through the rocks and at the ground surface, as well as dilution and dispersion of the radionuclides in large amounts of air, both in the rocks and in the atmosphere. Therefore, the release at the ground surface must be estimated from modeling of the relevant physical and chemical processes and knowing the activity observed at the monitoring stations, plus some information coming from the nuclear test site. This is what I call a scenario. The rationales for rapid scenario determinations following underground nuclear explosions is mainly to enhance NDC expertise by providing ATM with a likely physics-based radionuclide source term emitted to the atmosphere, which will be better than any arbitrary release of a fraction of the cavity source term. Advanced transport code developed capacity to depict various aspects of the complexity associated with the underground nuclear explosions, two phases, non-isothermal flow and transport with realistic 3D fracture networks, or condensation of radionuclides in the nuclear cavity. However, it will provide higher validity computations, but requires higher expertise modelers. Advanced transport code go with time-consuming simulations, even with HPC. However, they allow for slow construction of a knowledge base, and they can be used to validate simplified approach. Finally, advanced transport codes are not handy to shape scenarios and associated source terms on a trial and error basis. This is why we develop STM Toolkit, or Source Term Modeling Toolkit, a modular software package allowing for rapid and step-by-step construction of scenarios and their consequences in terms of emission of radionuclides following underground nuclear explosions. STM toolkits come with a user-friendly graphical interface, and there is no requirement for high expertise in any particular domain. STM toolkit provides estimation of radionuclide activity as a function of time from the nuclear cavity to the monitoring stations with 4 tools. Tool number 1 calculates the cavity source term. The user has a choice of relevant fission products among beta decay isobars from mass 72 to 171, which means about 800 nuclides. There is a choice of fissile materials and neutron energy, as well as the nuclear database. With that, as illustrated here for the xenon 133 decay chain, STM toolkit provides the time evolution of the quantities of all the nuclides in a nuclear cavity, here shown without any fractionation in a log-log plot with the time scale is 100 days. Here, my example is for a 150 kiloton nuclear explosion. Tool number 2 deals with the nuclear test configuration. The inputs come from data fusion and databases. We need to enter the yield of the explosion and its depth of burial, the nature of the rocks and their water saturation. The computations are made from empirical laws and parameters derived from former nuclear tests, and the outputs are the cavity radius, the height of the chimney, and the shortest distance to the ground surface. The pressure of water vapor in the cavity is derived from an equation of state. Following my example of a 150 kiloton nuclear explosions, here buried at 550 meter depth in a saturated granitic rock, we end up with a radius of 50 meter, a chimney height of 150 meter, and the gas pressure inside the cavity is about 50 bars. With that parameter, we can enter into tool number 3, which is the subsurface transport. It will give an estimate of the radionuclide inventory released at the ground surface over time. We consider 2 settings, either a borehole of a given radius with a potential delay before drilling, or a single fracture of a given aperture. Then 1D calculations will give the time evolution of the pressure in the cavity, both including surface venting and a seepage from the cavity walls, as well as the fraction of the carrier gas released at the ground surface. The convolution of this gas release and the cavity source term as calculated with tool number 1 will give the radionuclide inventory released at the ground surface. Still following my example of a 150 kiloton nuclear explosion buried at 550 meter, here is an example of the release rate of the 4 radioxenons as a function of time, as well as their precursors. And here I assume the release is from a fracture which is 250 millimeter large. So this is the, micron, 250 micron aperture, starting at the top of the chimney. Here, the 1D calculation we are doing are simplified equations, and so they assume a steady state, and an option of the code allows to calculate the time before which this assumption is not valid. So in our case here, as shown on the graph, this time is less than 4 minutes. Then we can enter tool number 4, which is the ATM preview. It will give an estimate of the radionuclide activities expected at the monitoring stations. It provides the volume activity from the conversion of the radionuclide release at the nuclear test sites. For this, we are using empirical determination of the dilution factors as well as the transit time obtained from a FlexPort simulation of series of releases from a site of interest. This is one becquerel over 1 second every hour from January the 1st to December the 31st, observed at nearby monitoring station with some statistical distribution. For these calculations, we are using real meteorological data, so we end up with real conditions for past reconstruction of events or realistic conditions for future events. Alternatively, we can obtain these dilution factors thanks to some simplified rules like analytical equations. Following my 150 kiloton explosion, as I presented before, I assume here that it happened at the Punggye-ri site in North Korea, and we are calculating the xenon 133 concentration activity expected at the RN38 monitoring station in Japan. And you can see in green the xenon 133 and 2 remaining precursors, in blue the iodine, and in dashed line the metastable xenon. If we compare with the minimum detection concentrations for new generations radioxenon monitoring system, we can see that we could detect in this scenario this explosion at the North Korean site in Japan between 1 day and 2 weeks. As a conclusion, STM Toolkit is a very handy and user-friendly software package for step-by-step physics-based source term estimates of all relevant fission products from the nuclear cavity to the monitoring stations. It uses realistic conditions from empirical laws and parameters with input from data fusion. It gives a rapid, less than some minutes, 3-5 minutes computations for trial and error determination of scenario and their source term before exporting them to atmospheric transport modeling. Work in progress is adding the fractionation of the source term by condensation in the nuclear cavity and allowing late time seepage from barometric pumping. Next, we will also do further confrontation of the code against documented situations. Future development could be the addition of radionuclides other than fission products and addition of other carrier gases. Also, acceleration of subsurface transport simulation in more complex conditions by machine learning. With that, I thank you for attention.